and K and N are isogonal conjugates. So is there anything special about the isogonal conjugate of the 9-point center? So yeah, actually, the cognita point. Okay. So let's draw the isogonal conjugate. Okay, so these are the feet of the altitude. Yeah, what's the best way to draw the isogonal conjugate other than reflecting rays? I'll just reflect all the rays. So draw AN. Actually, you know what? I'll do it this way. So these are the feet of the altitudes, and I can draw the pedal circle. JKL. Oh, you know what? That's kind of annoying. I'm going to just do it the old-fashioned way. So I'll draw this ray and this ray. And I'll draw the angle bisectors. Okay, so that's the cognita point. That's K. And then OK intersects BC at X. And OK, it intersects BC and AN at X and Y. But we want to be able to see the intersection better. So what if I make this like a really tall triangle? I think that's a isn't what the angle bisector? Oh, line AK passes through the circumcenter of BOC. Okay. So I'll draw that in just a second. I just want to figure out how to make this diagram look better. So that, yeah, something like this, I think is better. So OK intersects BC at X, but then it's hard to see where it intersects AN. No, K isn't the incenter. K is the isogonal conjugate. Oh, you're right. I did draw K as the incenter. Oh my God. I'm really silly. No, you're not stupid. I am. Okay. So we drew the two angle bisectors. Now I have to reflect them. It means they're isogonal conjugates. So this point is really the point K right here. All right. So this is really point K. And I was just being silly. So that's the cos neta point. And let me hide. I don't need to draw all this. That's a 9-point center. That's the cos neta point. Then I want to see, where does OK intersect BC? And where does it intersect AN? So let me see if I can draw a good diagram. I want to see the intersection with both. So if I draw something like that, I think that looks pretty good. Okay, so OK intersects BC at X, and it intersects AN at Y. Yeah, and you want to show X is the reflection of Y over that circle. So basically we want to show that XO, or YK times XK is OK squared, is what we want to show. Okay. Yeah, well, so I'll rewrite this because, yeah, not everyone knows this on watching my channel, but XK times YK is equal to OK squared. Oops. So that fix it? That didn't work. Oh, I'm just going to put this last little piece in LaTeX. You can't LaTeX just a piece of it, I guess. I'll leave it like that. It's good enough. So we can check it, because GeoGebra has a tool to do that. Yeah, it's true. Yeah, it does look hard. Especially because you have isogonal. Yeah, I mean, I'm always intimidated. But yeah. You guys want to try an easier problem? Yeah, I don't know much about the cos neta point. Let's see, it's almost 11 in my country. Let's try a middle riddle. See, and then we can come back to this. So, oh, I think this one was kind of interesting. Let's see, we have this. This one was also kind of interesting. Let's try this one for now. See how quickly we could solve it. So we reflect each, we draw the end circle and we reflect the tangency points through the midpoints. So okay. So D, E, and F. And we draw the tangency points. Oh no, those aren't the midpoints. Those are the points of tangency. Okay. So this is D, E, and F. We close this. And now we do the midpoints, and we get R, Q, and P when we reflect it over the midpoints. Oops. I just reflected a segment over a point instead of a point over a point. So these are going to be the X center, the X touch points, right? Obviously. So yeah, like really, it's kind of silly. Like really, I could just draw the X circles, but I'll just leave it like this. So this is R, and this would be Q, and this would be P. And then PR intersects DE at X, and DF intersects QR at Y. Hold on, I see the chat. DF intersects QR at Y. Okay, so I should draw rays for those. Draw a freehand diagram using a pen tool. I'll just stick with this for now. So and I want to show that A, X, and Y are collinear. So this is Y, this is X, and that's A. So should I draw the X circles? It would probably make it easier. I don't know why they word it like this. I should just say the X circles touch it at R, Q, and P. That'd be easier. But let's do this. So you can do it quickly. So Stefan taught me this trick. These will be the X centers right there. The in center and the X centers. And then we could draw the circles. So here's one X circle, here's the other X circle. And then the last one. Shrink it a little bit. Like this. So those are the X circles. Oh yeah, no, it's not an angle bisector. This is the in center. And probably, yeah. Let's see. It looks a little better, maybe. Call this Q, or I'll call it T. So it's true if and only if the cross ratio RAXY is equal to so AX and Y are collinear if and only if RA from D, the cross ratio ARXY is the same as from R, the cross ratio DAXY. And that's true from DRAEF is equal from R to DAPQ. Okay, so because of the Gergonne point, RAEF is harmonic. Wait, DAPQ. So yeah, you guys are way smarter than me. Yeah. But okay. All right. So yeah, the middle riddles, you don't even need the X circle. Oh, because the backslash. You don't need the X circles. Okay. So a D, so RAXY. Okay, so RAEF. So if EF meets BC at a point, then that point B, D, and C would be harmonic. But then how do you, so RAEF, so AR, okay, because where EF meets it is where, okay, I'll have to think about this proof a little bit more after the session. But yeah, there's a lot going on here. Yeah, explain it to me just a little bit. So we have R, A, E, F are harmonic. Why is that true? So I can just, yeah, so let the intersection of EF and BC be a point. And then project onto a line. So am I projecting through D onto the circle? Oh, I'm projecting onto this line right here. Okay, and that's harmonic because of the Gergonne point. Okay. That makes sense. And then this one is like the same thing, but in reverse. All right. So I'll move on to another problem. So that's another middle riddle. Maybe we could try a hard one since we're going through the middle ones really fast. Oh, this one's also a middle riddle. You want to keep working on this one? Or do you guys want to try the other? Or I could look for another hard riddle on the website. What do you guys think? This one looks too hard? Okay. All right. Let's see. Let's see what's here. So Oh, I already did this one on a previous time. This one was kind of interesting, but it has two mixed linear incircles. So easy to breathe. So yeah, this one has two mixed linear incircles. So it looks like it could be challenging. So yeah, I don't know if you guys want to try this one. So yeah, basically just show the bisector of angle XAY. It passes through the centroid of the X central triangle. That sounds kind of hard. To me, it sounds kind of hard, but let's see this one. This one looked kind of interesting. You just have a triangle and then you have the midpoints. Oh, I think I might have done this problem before, actually.
Yeah,
but I
we
don't
did
think
it before.
we did this one before, right? Yeah.
Yeah. I think I even wrote the solution in the Discord, our Discord.
Oh, really? Yeah. Oh, now I remember. Yeah, I remember reading it. That was a long time. Yeah. Uh, this one looks very hard. There was one nice one I saw. Let me see if I can find it. So So we have the incircle tangent at D and F. EF intersects AI. This is a lot of. Let me see if I can find something. Oh, I think we looked at this quick. BC and AH. So we have ON intersects the circle at K. At S. Now let me try another one. Let's see. Maybe this one's interesting. So X and Y are in DB and DC. So that ADXY is cyclic. And then we draw the orthocenters of DBC and DXY. Okay. And then we draw the perpendicular from B to H prime H intersect AY. Okay, so H prime H intersects AY. Oh, the perpendicular from B to that intersects AY at W, and the perpendicular from W to BH intersects AD at R. This looks kind of interesting. Have I done 313? Let's see. I have not done 313. I could do that. So P. So we have the radical axis of these two circles. That's kind of interesting. I'm gonna do this one. Yeah, thanks. So GeoGebra Classic. All right, so this is riddle 313. Sorry. Actually, it might be yeah. So P can be any point, and it intersects AC and AB at X and Y. I'm gonna do it like this just so it's easier. So this will be x and y, and that'll be p. So this is point P. And then we draw the circles, the center A and radius AB, and A and radius AC. And we want to see where BP and CP meet those circles. Okay, so this is Z. And this is T. And we want to show the radical axis of BYP and CXZ passes through a fixed point. So if I want to draw the radical axis, yeah, what's the best way to do that? I forgot how to draw the radical axis. Isn't that crazy? Like I could draw a third circle and but yeah, what's the best way to draw the radical axis of two circles? So I guess I could do this. So if I take the midpoints, so I think this is the best way, right? Because the midpoints of these lie on the radical axis, and the midpoints of these lie on the radical axis. So HI is the radical axis. I think that's the best way to do it. So I'm going to hide all that. Okay, so basically it's saying that it's saying this line passes through a fixed point. Let's see, we could try to do the trace and see where that point is. So this point right here, okay, let me make this nicer. And I'm gonna get rid of the trace. So yeah, somehow when I move y and x around, this goes through a fixed point. Yeah, I wonder what that point is. I'm going to show the trace one more time. It seems like it has to be like some kind of triangle center, right? It's not the orthocenter. It's not the circumcenter. What would this point be? It's like right here. It's around here. What other triangle centers are there that could be? I don't know. It's not the incenter, not the circumcenter, not the 9-point center. Unless it's like the Feuerbach point or something, which I don't think so. That'd be really weird if it was the Feuerbach point. Okay, let P be a special point. Okay. What point do you want P to be? Maybe I could try it being like the in-center or something. Yeah, what if I make P the orthocenter? Then the radical axis would just be the perpendicular, right? At least it looks like it. Okay, so it lies on the altitude from A. Yeah, so we're trying to see if we can figure out what the point is. So we could draw the altitude from A. It's probably so yeah, this point I, well, no, that's got to be a coincidence. Yeah, whatever. Maybe it might be nicer if that point's like inside the triangle. What if I draw like an obtuse triangle? Yeah, I feel like that might be a little easier. If it's like an obtuse triangle, and then the point is inside the triangle. But let me make, there we go, that's better. That's easier to see. And then this would be the point. So what's special about point J? Is the isogonal conjugate of J something special? Maybe ABJ equals ACJ? Or ACB? No, I don't think so. Let me just make sure that's actually the point. I think it is. Oh no, that's not the point. It doesn't necessarily lie on the altitude. See, I got confused. It's all the way down there. Okay, let me delete this altitude then. That's just making things confusing. So the point, it's like right here. Is it on the angle bisector? All right, see you, Ruben. Have a good one. Oh, does it lie on the median? Sorry, I missed when you said that. Okay. Let's see. It might. See if it lies on the median. Oops. So here's the median. And let's draw the trace of it. Let's draw the trace of the no, oh, it doesn't. Okay. Are you sure about that though? So it's like right here. Boy, if it lied on this median, let me see. Yeah, I think it lies on the median. Okay, so we need to draw the median, and that is where it should be. Yeah, A, B, and C aren't symmetric. It's just, yeah. Is it the midpoint of the OP? The midpoint of AJ? I don't think it's the midpoint of AJ, but oh, the midpoint of the median chord. Yeah, maybe it's the midpoint of the median chord. So is that like the Humpty point or the Dumpty point or something? That's the Dumpty point. Ah, it looks like it's the Dumpty point. Yeah. Yep. So I think that's it. I think it's the Dumpty point. Is the okay. So yeah, let's draw the Dumpty point, and then we want to show that so we want to show the Dumpty point has the same power with respect to both circles. So yeah, I don't even need to draw the radical axis anymore. Now that we know it's that, we can try to show that that has the same power with respect to both circles. Well, actually, I can keep this. I just don't want to draw it that big. So I think, yeah, these are all cyclic. And I can draw this circle too, because sometimes it's helpful. Sending BA to AC. Oh yeah, because Yeah, so basically, yeah, the circle BKC is tangent to AC, and the circle CKA is tangent to AB. So this is tangent, and this is tangent, right? That's the property. And then from there, it follows that the spiral similarity that you're saying. If we let P equal A, then we know the special point lies on the median. Okay, so we have to show K has the same power with respect to those two circles. Let's see. So how would we find the power of K with respect to this circle? So is it worth drawing the center and then saying it's KL squared minus the radius squared? So yeah, as X moves along this, does K always have the same power with respect to this? Because this one doesn't change. Yeah, so we're saying K always has the same power with respect to this, right? So that's pretty important, right? Like that seems like it shouldn't be that hard to show, right? So yeah, then the question is just where should we let X be to find the power? And then how do we just show it's always the same? So this goes through C, X, and Z. Oh, it must be KA squared. Oh, how do you know it's K? Oh, because if I set X equal to A, then it's tangent. Okay. So we need to show wherever I move X, the power is always KA squared. So basically, if I draw this circle, I mean, this would pass through the tangents from K to that circle. So it'd be orthogonal to it. So yeah. So basically we're saying these are always orthogonal circles, right? Which is interesting. So OA, so we need to show OA is perpendicular to AL, right? So, wait, is that true? No. But yeah, we need to show they're orthogonal. And, oh, so there's a property of the Humpty point, I'm sorry, of the Dumpty point, which says that basically this, actually now I'm confused. So if we set the point X equal to A, then this circle should be tangent to, but I thought that was a circumcircle of KAC that should be tangent to AB. Actually, now I'm not sure. Yeah. So yeah, KA squared is KB times KC. But so if P equals K, then K, oh yeah, we have to move both of them to make P equal K. But it's, I still don't understand that, because if we set P equal to K, this circle isn't tangent to that, right? So I'm still a little confused. So I guess what we could do, oh, but the power of K would be KA squared. I think it's more if P equals Y rather than P equals K. It's just saying that we can get this to be tangent. Yeah. So yeah, we want to show it's KA squared. We can just delete Y. Yeah, we can just delete Y and focus on X. I agree. And yeah, we don't need this circle. Yeah, really all we need is, yeah, we just want to draw the Dumpty point. What is P? I forgot what. Yeah, we don't need P. I mean, I'll just draw a B in, but yeah. Really, yeah, we're just saying whenever X moves, K has the same power with respect to this circle. And wait, let me hide this too. And we want to show it's KA squared is the power. And that's the same as the power of K, yeah, with respect to AB, with respect to ABC. Wait, that doesn't make sense. Oh, K's, okay, because the power of K with respect to ABC is the negative of with respect to this circle. I was going to say, because otherwise I would think it would lie on the radical axis. Yeah, powers can be negative, yeah.
Wait, so we can use the radical axis of the circle with the radius 0, maybe?
Maybe. So this circle right here, and we could show it's on the radical axis of this and this. That's possible. Oh, yeah, it's possible. Yeah, this feels like it should be easy. My brain is just tired, but yeah, we just have this circle and we want to find the power of k with respect to this circle. And show it's always the same. So yeah, we could try that. Like, so k should be the radical center of a prime, a, and this circle, I think. So yeah, maybe we can use point circles. Basically, I think k should lie on the line connecting the midpoints of these two. So yeah. Yeah, so k is the radical center of the, whoops. Well, yeah, I don't need that. K is the radical center of this point circle, and this circle. But yeah, we have to prove that. We have to use that AZ equals AB. I think that's the missing thing that we haven't used yet. How does that prove it? I don't think that, or I don't see a proof right now, but. K lies on the radical axis of A prime and CXZ. Oh, how do we know that? Or how do you know that? Because yeah, if you can show that, I think it would solve it. Oh, no, I didn't prove that. Sorry. So we have the power of B with respect to that circle. Maybe it looks a little easier to calculate because it would be bx times bz. And the power of A with respect to the circle is ax times ac. So maybe we could use like the power ratio lemma or something. Okay. A prime. Okay, so do you want to draw the antipode of A? So with respect to CXZ, the antipole of A. So what is the antipole? So if I draw the pole, so this would be the antipode, right? Let's see, how do I do pole and polar? Oh no, I think he means the polar of A with respect to that circle. Yeah. Yeah, the polar. This is the polar of A. Yeah, it's okay. So how do we know A prime lies on the polar? Yeah, so you're saying A lies on the polar of A prime and A prime lies on the polar of A. But how do we know that? So I guess it looks like this point's pretty important right here. Is it because this is a symmedian? Yeah, okay. So this, well, actually I don't see how that proves it. So yeah, how do we know that A prime lies on the polar of A? It looks true. Basically, it looks like AE is the polar of A. I just don't know how to prove it. So, or A prime E. So So should I draw these tangents like this? So yeah, these are all collinear, but I just don't know how to prove it. Okay, so Khan said CXZ passes through a fixed point on KC. Oh, is AN always tangent to the circle? I think it is. Is that obvious? So AN is always tangent to the circle? Yes. Okay. So that seems pretty important. Okay. HM and AE cuts L at F. What is HM? Oh, AZ cuts the circle at F. Okay. Then FC passes through E. Is that obvious? Because AZB equals ABE equals ACE. Okay. Okay, so it's an angle. Okay. So those are collinear. And then A prime BC, yeah, it's harmonic. And then you project through E. Okay. And maybe you project onto AZ. So AZF project on AC and AZ. And that's kind of how we get that those would have to be harmonic. So that's how we know that's the polar. Okay. Interesting. Okay, so that's how we know it has to be the polar. And I think that solves it because then A prime lies on the polar of A, right? And A lies on the polar of A prime. And then what do we, let's see. And take the midpoints of AM and AN. So that's the radical axis of the point circle A with this, right? Okay, so we want to show K lies on that, right? Oh, but because A prime K is the midpoint of that and that and that, so it's obvious. Okay, so K lies on the radical axis of A in that circle, and so it always has the same power. I like it. All right, perfect. So I'm gonna type it up. We probably have just enough time to type it up and win. So let well, but yeah, we don't even need to know that AN is. Oh, but we do we need to know that AN is tangent? I think we do know it though, because we kind of assumed. I don't know if it matters. Okay, so all right. So let AZ cut. Let AZ cut. CXC at F. Then F, E, and C are collinear. So is E in the problem? So let BZ intersect ABC at E. Then I have your angle chase. So your angle chase proves that they're collinear. So let K be the A dumpty. So first I'm going to define K. So let K be the A dumpty point. And yeah, it's a fun one. So we have this. Whoops. And that implies FC passes through E. And then we have the harmonic. So A, B, A prime, C is harmonic. And then projecting sorry. Then we project through E onto AZ and AC. C. Then we find that A prime E is the polar yeah, we find that A prime E is the polar of A. All right. Once we know it's the polar, that means that A prime E passes through the tangents from A to the circle. From A to CXZ. And then I'll say call them M and N. N. Then A prime and M are collinear implies, or I'll say let R and Q be the midpoint of AN and AM. So then KR and Q are collinear. Q are collinear, and that means that K lies on the radical axis of the point circle. Point circle A and CXC. And that means that K lies on that radical axis, then KA squared is the power of A. Power of A with respect to CXZ. And then similarly, K squared is the power of A. I have to retype it because copy paste messes things up. A with respect to BYT implies K. So implies the radical axis of I'll just write as this ever. The radical axis of BYT and CXZ passes through K as P moves. All right, so that will finish it for today. Let me just make some more room so that we can see everything here. So yeah, I'm not sure if this is the same idea you had, Ravi, but it looks really cool. So thanks everyone for participating. I know it's a long session, but we had a lot of really great solutions today, and a lot of these problems are not that easy. So I really appreciate everyone participating and helping make my channel great, because I know it's more you guys than me. So I appreciate that. So for anyone watching, if you want to join us next time, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.